Okay, I'm back. So I think it's time to do some sketching of the derivative, which seem to have been giving a lot of people some trouble. So hopefully this will help. We'll find out. So looking here, certainly the start. We should take a page from back here where I was asking you this question. It says if the function has a local extreme at c, then what is the value of f prime of c? And it was 0. So, I mean, that's a really helpful place to start, is to go right to the maxes or mins of a graph and then know that the derivative is 0 there. So looking at this first guy, we see that local min at x equals 1, 2, 3, 4. So the fact that there's that local min of 4 gives me a pretty solid footing to say that the derivative there is the slope of that tangent line. That tangent line's horizontal, so it's 0. So right at 4, I know my derivative is going to equal 0. Now from there, I'll just pick out a few more points, maybe that point there. And you got to try to draw your tangent line as carefully as possible. So for example, if you drew your tangent line like this, I did too good a job on my first try. I was trying to do a bad job. What I meant was, if you drew it like that, I hope it's pretty obvious that that's not tangent. I mean, that's hitting the graph and then it's hitting again later. That just doesn't really follow the right trajectory. So let me straighten that out. It should really look a lot more like that. And again, a good way to think about this is like to zoom super close in on the graph, and you should just barely be touching it. So looking here, if I zoom in just on a little bit of the graph, I want to follow that little tiny bit of graph. You don't need much to sort of see what it looks like. And now that I'm super zoomed in, I can actually see that I haven't done that great. Like, it should probably be a little more like this, following that and then following that. And so mine is actually off. Like, it doesn't look like I'm off by much, but if you stretch that out, it is kind of a big difference to be off by. But I hope that helps you guys to sort of picture what it looks like. Imagine if you could really zoom in really close and just take maybe an inch on one side to an inch on the other side, then that's going to look pretty linear, and your tangent line is going to follow that line. So imagine turning a little 1-inch line segment into a full-blown line that stretches to infinity, and that's what a tangent line should feel like. So again, I'm going to go ahead and admit, I think this line I drew is not that great. And I'll give it the old twisteroo, make it look a little better. I think that might be how it was the first time. Anyway, now that you're looking at that, how do I actually pull the slope off of that? Well, I gave you a couple of easy benchmarks. We should know that from corner to corner along a square, that certainly is what a slope of 1 looks like. And of course, that's because we're rising 1 and running 1. And rise over run, 1 over 1 is 1. Don't forget, I told you that's going to look like a 45-degree angle every single time. A slope of 1 is sort of a 45-degree angle. So anything steeper than that would be more like 2, 3, 4. Anything shallower than that would be more like a half or a third or whatever. So we can eyeball these things, but honestly, we're kind of past the point of just eyeballing it. We do need to be a little more specific. So if you're trying to be really specific, then you got to get in there and look at points. And looking at my line, it does seem to be about exactly 1. I mean, I can pull a couple of points off this tangent line. Like, I'm basically here and here. I am rising 1 and running 1. So if this was 4, then over here is 6. So let's go over to 6, and I feel pretty confident in saying that my derivative is 1. Now, I were to exploit symmetry here. I went 2 to the right, so now go 2 to the left. Look at this point. Since my graph is a parabola, this guy over here that had a slope of positive 1, I feel pretty confident saying this slope is just going to be negative 1. It's going to be sort of the mirror image of the other line. And then lo and behold, yeah, we're going down 1 over 1. So 2 points left at positive 2, we're getting a slope of negative 1. And roundabout here, you can see that our derivative is just going to be the line that passes through these 3 points. So boom, ba-dum, ba-dum, and boom, ba-dum, ba-dum. That's your derivative. This is f prime of x. Let's do a harder one. Okay, this one's not even a harder one. The first thing that I hope sticks out is the fact that at -1 and at 3, we have nodes. So you should be expecting that the derivative is not going to exist in those two places because we're not differentiable over here. So we'll get no derivative over here. Does that mean it'll be a vertical asymptote? Or does it mean it'll be a hole? Or does it mean it'll be like a jump discontinuity where we come in from one side, leave from somewhere else? Who knows? Let's think it through and see what happens. So looking here, since this whole section of this graph is linear, that means every single point on here, the tangent line is literally the graph itself, and we can find that slope. We see that we are going down 2 and right 1. So in terms of a slope, it's -2. So starting from -1, my slope is -2, but at -1 I don't exist, so I'll put a hole. But everywhere left of that, I'm constantly getting -2, -2, -2, -2, -2. So my derivative function should just be a horizontal line there. Then I get to this green chunk of graph now, and that guy's horizontal. So all the tangent lines there are horizontal, and of course the slope of a horizontal line is 0. So that means at -1, after having all these slopes of -2, now my slope is 0. And it's 0, 0, 0, 0, 0, until I get to 3, where I'm not differentiable again, so I get another hole because my derivative is undefined. Now looking at the lavender colored section, we have an increasing function with a much less steep graph than the orange part. So this guy's derivative we can see is we're rising 1 and running 2. So that's a slope of 1/2, and it's positive 1/2, which means from here you'll just hop up a little bit to 1/2 and show that as a constant derivative. But that's it. I think that's sort of one of the easier ones to sketch because you know that when the original function is linear, the derivative will just be constant. It'll just be a bunch of horizontal segments, which, to me doesn't feel so bad. All right, how about this one? All right, again, if I were you, I would look first at these two extrema. Those are occurring at -2 and at 5. So I know pretty immediately that I can go to -2 and I can go to 5, and my derivative at both of those places is going to be 0. So I got two pretty quick points that I can place very confidently on the graph of h prime. The next point that I would go for if I were you would be right smack dab between these two. So what number is right smack dab between a -2 and a 5? Well, the middle would be the average, right? So add them up, divide by 2, and you get 3/2, which is 1.5. So at 1.5, my graph has this special point here. And I mentioned this before, and I'm going to mention it again, but if you look to the left of this purple point, then my graph has a feature that I definitely said in class at least once. It's called concave up, right? This graph opens up. But at some point, the graph flips over and starts to open down, right? And I hope you agree, you got to agree, that the place where we flip over, so to speak, is right here at the 1.5. And that point is called a point of inflection. You don't need to know that as vocabulary. I'm just giving it a name. But this is called the point of inflection. And the interesting thing about that point is that point represents the maximum or minimum of a derivative. So if you look at the tangent lines on either side of this point of inflection, over here we were flat horizontal. That's a derivative of 0. Then we got a little steeper and a little steeper, but right at the point of inflection, that's when we were at our very steepest. Then we hit the pink section of the graph, and suddenly we're getting less steep, less steep, less steep. So that tells me that this point of inflection corresponds to a maximum value of my derivative, because I went from 0 and I got bigger, 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 but then I got smaller, smaller, smaller. So at 1.5, I should get a maximum value to my derivative. And by the way, that maximum value seems to be, geez, I don't know. This is the part that some people were struggling with. So let me help you eyeball this again. And again, when I say eyeball, I really don't mean estimate. Like, you really need to be pretty darned accurate. So let's play the zoom in game again. 400? Sure. So if I zoom in really, really closely on this, then hopefully you remember the point we were talking about was at 1.5. That's right here. If I kind of run along the function here, then this line is my tangent line. I'm so zoomed in that it seems like I'm just riding along the function, but really there's a tiny difference. If I get out to here, we see that we deviate from the graph. If I keep going, then out here we start to deviate from the graph. But here I'm following it really closely. So now pick a couple of points. I don't see any that are like very well defined, but I don't know, here to here. Hopefully you can see that we're going up. It looks like it's a little more than 1, but we're basically going from the halfway point to the halfway point. That's a change of 1. And the horizontal change is 1. I think it's safe to call this slope pretty much exactly 1. Maybe it's a little bit steeper. Maybe it's more like 1.5. But there's wiggle room here that I can allow for. But if I were you, I would definitely be plotting my derivative at about 1, maybe a little bit higher. But you shouldn't be up at like 3. You sure as heck should not be up at 5. We should be like 1-ish. So plot that point. And honestly, at this point, you could stop because you should know that this function is a cubic function. And if I differentiate a cubic function and its degree goes down by 1, we're going to get a quadratic. And having these 3 points and knowing that I'm quadratic, meaning a parabola, I'm done. I know that my graph now just has to be a downwards opening parabola that passes through those 3 points. So it should look something like that. And I'd be perfectly happy if that's all you did. If you plotted the 2 zeros and roughed in where the maximum value would be, and if you sketched a parabola because you knew that the derivative had to be quadratic, that'd be great. Let's do 12. Oh, 12. All right, so 12 is the one where we have to go in reverse, and a lot of people really weren't so hot at this. So I'll do it, and then we'll see how it goes. But reading it, it says, given the graph of J prime, notice this time we're going in reverse. You already have the derivative. You have to work backwards to the original. So what does that mean? I don't know. Just reading, they give you a couple of points for free. It says we definitely pass through 0, -3. So I'd plot that right away. We definitely pass through 5, 0. So that's right there. So you got those 2 points for free. Now, everything you knew about what we did before, you need to reverse it, right? Remember before when the minimum value meant the derivative was 0 and the maximum value meant that the derivative was 0? We'll reverse that. When the derivative is 0 means we get mins or maxes. So that means when my derivative is 0, those 3 points, that means at 2, I'll be getting a min or max. And at -3, I'll be getting a min or max. And at -6, I'll get a min or max. By the way, that's a question down below. It says, what values of x will be the extrema of J prime? Of plain old J of x. So x equals -6 will be an extrema, and x equals -3 will be an extrema, and x equals 2 will be, and again, how come? Because the derivative is 0. Oh my god, derivative is 0. Oh my god. Okay. So that doesn't seem super helpful just to know that maxes or mins occur here. I'm realizing now that I drew dots. I shouldn't even be drawing dots. I should just be marking, sort of marking like this is a special location. This is a location. This is a location. So we'll put actual points in later. I'm just saying, I know there's kind of a landmark here. I'm going to have a max or min here, and I'm going to have a max or min here. But let's say it's a max. I have no idea how high it is. Is it up here and I'm kind of concave? Or is it way down here? Maybe it's way down there. I don't know. We'd have to keep investigating to find out. So what else do we know? I want to talk about D, I think. D says, hey, take these three extrema and now actually classify them. So if x equals -6, what is that? Is it a max or a min? Well, think about what's happening over here. At -6 to the left of that, my derivative is negative, right? Because it's under the x-axis. Negative derivatives mean that the original function is decreasing. So I must be decreasing. Then when I get to -6, my derivative is 0. And to the right of that, my derivative is positive, which means the function is increasing. So I decreased, got to this x value, and then I increased. So you tell me, what kind of point is that? That's a min. Right? We know it's a min because we went from decreasing to increasing. Now by the same token, as I approach -3, the derivative is positive. So we're still increasing. But then we get to 3 and we're 0. And then we're negative, which means we're decreasing. So to the other side, we're decreasing. That seems like pretty hard evidence that at x equals -3, the original function has a max. And then just do it again. I'm now negative, all the way to 2, which means all the way to 2, I need to keep on decreasing. And then after 2, I can increase because I'm positive. So from there, I would go up. And so that tells me that x equals 2 is definitely another min. And by the way, I have a graph now this graph's fine. We could use this graph. Notice I did happen to pass through the 2 points that I needed to pass through. And I do have a local max right where I'm supposed to have one. I have a local min right where I'm supposed to have one. I have a second local min right where I'm supposed to have one. Is this the exact right height? Like, should it be at -2? No, it doesn't need to be. It could have been lower. It could have been higher. It doesn't matter. All I need is for you to have the right trend. And trend means the graph decreases when it ought to decrease, and it increases when it ought to increase. And all the important points are at the right x values. So this is fine. And so finally, just to use the last bit now, I kind of talked about already, but on what intervals will the function increase? Well, j of x will increase whenever the derivative is positive, and it's positive between these two values because it's above the x-axis. So we're definitely increasing on the interval from -6 to -3. And we also increase on this second interval where the derivative is positive, which is from 2 to infinity. Now, if you're looking for where the original function decreases, then you look for where the derivative is negative. Negative means you're below the x-axis. So -infinity up to -6 seems to do the trick. And we also decrease from here to here because, again, when the derivative is negative, notice I'm not looking at the decreasing and increasing part. I'm just looking to be under the x-axis. So this is negative. That means the function decreases between those values. So between -3 and +2. All right, that's it. Moving on. So finally, there's number 13. And 13 just wants to know, hey, is this the right derivative of this graph? And there's a few things I'd want you to mention. You're certainly going to say yes, first of all. Now, why? Well, there's a cusp here. You should probably use that vocabulary to say that because there's a cusp at x equals 0, the derivative should be undefined at x equals 0. Now, we end up with a vertical asymptote. That's definitely undefined. So, yes, m prime of x should be undefined at x equals 0 because m of x has a cusp. Okay, and what else? Well, we see that our derivative is negative on this entire interval from -infinity to 0. And that should make sense because the original function is decreasing, 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 decreasing along that whole interval. So you could say m prime of x should be negative on the interval from negative infinity to 0 because m of x is decreasing. And then you could say the same thing about the other side. On this side, the derivative is constantly positive, positive, positive because the graph is increasing, increasing, increasing. I won't bother saying that. But the one last thing you could say is maybe just hitch a couple of points onto here. So 1, 2, so -3 seems to have a pretty clear-cut point of intersection. My tangent line seems to be doing one of those. What's the slope here? It looks like I'm rising down 2 to run 4. So if I'm going down 2 to run 4, that feels like -0.5 to me. And then lo and behold, at -1, 2, 3, oh, would you look at that? The graph is exactly at -0.5. So if you just kind of spot check a couple of derivative values, then that seems good. So what else? This same point over here would be symmetrical. We can tell that's going to be +0.5 on the other side. So +3 is giving +0.5. Yes, it is. Again, this question, I just wanted to see you kind of flex your muscles and say all that you can say. And you should certainly be able to say that it makes sense for the derivative to be undefined at 0 because the original function had a cusp at 0. It made sense for the derivative to be positive on the right-hand side because the function on the right-hand side was increasing. Just basically make those connections, okay? So next was just 6 more of these, and I don't know if anybody wants to actually sit through that, but maybe you do, so sure, I'll explain them all one more time. No harm in it. Hey, look in here. I see another min. I'm a simple min. I look for a min. I plot 0. So at 1, we're certainly getting a derivative that's 0 because the slope of the tangent line is 0. Then I see another pretty clear-cut point right here. That guy's slope is pretty steep, looking like that to me. And it looks to me like I'm rising 2 to run 1. So that's a slope of 2. So at 2, I'm saying slope of 2. Then again, I can kind of use symmetry. If I go to this point here, I do expect this slope to just be the exact opposite of the slope on the other side, and it is. We're going down 2 and over 1, so that's another slope of -2. So at x equals 0, we're getting -2. And again, the derivative of a parabola should be a line, so just connect those dots with confidence, knowing that your derivative should be that line right there. That's a pretty easy one. This one got a lot of people a little bit. Again, you should certainly be noticing that there's a discontinuity at 2, which should mean that the derivative doesn't exist over here because we're not differentiable. Now, does having a vertical asymptote mean that we have a vertical asymptote over here? I'm not willing to say that. It might just mean, who knows, maybe it just means we have a hole and the graph does one of those or something. But if you look at the behavior of the graph, it should actually be pretty clear that here at 0, we've got a slope that seems to be about -1, but those slopes start to very quickly get steeper and steeper and more and more negative. So if 0 is giving a slope of -1, then as I approach 2, those slopes do just drastically start to go down and down and down and down and down, such that it definitely seems like the behavior is asymptotic, which would make sense. So it is. By the way, while we're saying all that, bring that over here and do it again. We just plotted the point at 0, so if we plotted that same point right about here, then that tangent line again seems to be giving about a -1. So if I flip over to 4, we're at -1 again. And if I look between 2 and 4, then those graphs are getting more and more and more negative, negative, negative again. So these guys would be going down, 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 down. And so what we're actually starting to see is that the two derivatives on the left and right are going to be mirror images of one another. So what's happening at like, I don't care, here, sure, at -1, I have a less steep slope. I was getting 1 at 0, but here I seem to be getting more like -0.5, so I must be at 0.5. If I go further out, then my graph is now even less steep. It's almost horizontal. That slope there might be like, it might be like a quarter. Let's just call it a quarter. So it's like here. But they're all getting closer and closer to the x-axis, which makes sense because the trend among all these tangent lines is they're getting close to horizontal, but they'll never truly be horizontal. So all my slopes are going to be negative, but never be 0. And so we can tell that that means our derivative function has a horizontal asymptote at 0. And we're sort of stuck behind that horizontal asymptote. And the same thing happens on the other side. So this blue thing is literally just the mirror image of the green. So just take that, reflect it over. That's pretty badly drawn, but hopefully you get the gist of it. It should be basically the branch of a hyperbola, and then the second branch of the hyperbola mirrored over onto the other side, like that. That's a pretty good one. I thought that one was a little more complicated, but certainly attainable. So I hope you understood that. Number 3. 3 is also pretty straightforward. It looks like it's kind of doing something weird in the middle. I don't love that. So what's the weirdness in the middle? It doesn't look like it actually lies flat to me. It looks like it actually comes up to a bit of a max before going down to a bit of a min and then going back up. And so if that's the case, then we have a kind of a much more complicated graph. If our graph just came up, leveled off, and then kept going, then we'd only have sort of a single important point here to think about. But if it does what it kind of looks like it's doing, then we have a max, then we have a min, and in the middle we even have one of them points of inflection that I was talking about. Suddenly there's like 3 points here to actually be pretty concerned about. So I don't know. What do you think they were doing? Do you think they wanted this thing to come up and have a max here and a min there and a point of inflection in the middle? You'd have to really zoom in on it for that to be the case. So I'll just make the command decision and say no, that's not the case. Why don't we just go ahead and say that what's happening here at, I don't know, -3/4 is that's the point where we go completely flat. So the derivative there then is 0. So at -3/4 we are getting 0. Then what happens to the left of that? To the left of that, my derivatives are getting a little more positive, more positive, more positive, until they're very, very positive. So as I go over, I keep getting numbers that are bigger, 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 bigger. So I believe my graph should just be coming down like that. What's happening on the other side? Well, on the other side, my derivatives keep getting bigger and bigger too. At first, they're only a little bit big, then they're bigger, then here they might be really big. So again, they just kind of go up and up and up and up and up. So it looks like my derivative function overall is just another quadratic. It's just another parabola, which should make sense because the graph of f of x here is definitely something you should recognize as a cubic. So it makes perfect sense for the derivative to be a quadratic with a G. Quadratic is spelled with a Q. Exclamation point. But that's your derivative. Again, just make sure that you're showing your minimum in the right place, which is nearish to -1. Okay, then there's this graph which I didn't love, and I talked about why I didn't love it, so I'm not going to talk about it again, but I certainly see us achieving a max right here. So at -5 we should be getting 0. There's definitely a min right here at +5, so that derivative should be 0 too. And then what's happening in the middle? I was horizontal, but as I go to the right a little bit, now I'm negative, but kind of small. Right here in the middle, I'm negative, but kind of big. What am I doing? If I go, I'm going down 2 to go over 1. So at 0, my slope seems to be about -2. And in the middle, I was here I was 0, and then I was getting negative, more negative, more negative, but the most negative I'll ever be is here. So it seems like the graph's just doing one of these. And then on this side, I was very negative, but again, I start to be less negative, less negative, less negative until I'm 0. So the graph goes burp and comes back up. Now my temptation here for sure was just to go, oh, okay, this is a parabola. And so just continue the thing up pretty quickly. But the graph doesn't really behave that way, so let's look more closely at it. If you look at what's happening after 5 and negative 5, meaning here, the graph is growing much more slowly than it was before. So this is 0, and the graph does turn over to give positive values, but those positive values grow pretty slowly. So they're going to kind of branch out like that. And then here they're going to go burp like that. So it should be more concave down here than concave up. Concave up implies a pretty quick growth of our derivative, and our derivative is growing slowly. So it should be more concave down. But for sure that's the derivative. And hopefully that makes sense. There you go. 5 looks like another no-brainer. By now you should certainly look at that and go, well, that's an x squared. So this is going to be an x. And you know that your graph is just going to be a line. So then it's just a matter of saying, all right, horizontal tangent line right there at 3. So 3 is definitely giving me a slope that is 0. And to the right of that, I have very steep slopes to less steep slopes to less steep slopes to 0. So I should be negative and coming up on that point. And on the other side, I'm 0, and then I'm a little bit negative. What have I done? Yeah, I'm silly. Let me just start that completely over. What I meant to say was that, of course, over here, my slopes are very, very positive. Those are increasing. That's a positive slope. And then it's less positive to finally 0. So we'd be very positive coming down, 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 down to that point. Then on the other side, now I'm a little bit negative, more negative, more negative, more negative. So it's just going to continue back down. Now I'm being very sloppy right now to make a point. I drew a line, and it's positive where it's supposed to be positive. But is this the right sort of angle for my line to be? I am expecting you to pinpoint these slopes more accurately, remember? So let's go do that and see if my rough sketch aligns with like the truth. And so I'm going to zoom in a little better and pick a point. Maybe that guy there. So my tangent line should be going something like this. That is now a pretty accurately drawn tangent line. And I can see that I'm going down 1, 2 to go over 1. I guess I trust that value. Sure, we'll call it -2. So I hope I didn't get this right by accident. But at -1, yeah, -1, we should really only be getting about -2. Which means that over here we should only be getting about 2. So in my rush to kind of do the problem quickly, I would say I drew my derivative graph too steep, and I would definitely say that is so steep that you'd lose credit for that answer. If you gave me that blue line, it's pretty close, it's pretty damn good, but we definitely have the ability to be more accurate. So if this was like a 2-point problem, then I would say for sure you're losing half a point. Maybe that doesn't seem like a big deal, but maybe it does. So just be really cautious and really try to be as accurate as you can as you eyeball the slopes of those tangents. Okay, just one more. And I think this is another pretty straightforward one because again we've got extrema that we can look at. So 0 again is giving a slope of 0, so 0 is 0. 2 is another point that's giving a slope of 0, so at 2 we're getting 0 again. Now between 0 and 2 at 1, we have another one of those inflection points where we go from being concave up to being a graph that's concave down. Those inflection points mean that if my slope was 0 and it got bigger, 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 this is the point where my derivative will be the biggest it'll ever be. And when I talk about big, What is that? We said we're supposed to be able to eyeball this, so one more time I'll walk you through how to pretty accurately get that derivative value. So you kind of, again, you want to be thinking about zooming in and then just follow that line pretty closely. So we were here, we're here, and if I follow this graph closely, up and out, and if I follow this line closely, down and out, then you'll notice we're probably here from here. So we're rising 1, 2, 3 to go over 1. We're not rising 2 to go over 1. If we rose 2 and ran 1, then we'd be at a second point. That's not a secant, that's not a tangent line, that's a secant line. It passes through the graph 2 times, right? So we know we have to be a little higher. That's why the better slope here is 3 over 1. So with all that said, when you go to graph that point, you better not put it at 2. It really needs to be up here at 3. And then what else is happening? Well, honestly, you don't have to do much more, because again, I find myself looking at a cubic function whose derivative I know is a quadratic function. And I've got my 3 points. This is my max, so just have this graph open down now. This parabola should be pretty skinny. Make sure you made it nice and skinny. That's it. We did it. We did all of them. And so hopefully these 55 minutes or so of review get you where you need to be in your understanding what you need to do. Hey, if it was helpful, there's really nothing killing you, nothing stopping you from putting a comment down there that says, hey, that was nice, thank you. Again, if you don't want to have sort of a permanent thing like that on the internet, then maybe just in class tomorrow, come up to me and say, hey, Mr. Ever, it was really great the way you took 2 hours out of your life to make this video for me. It was really helpful. That feedback, it does mean a lot. I don't really like making these videos. So if I don't hear from people that they really like them and that they're actually helpful, I'll stop doing them. So if you don't want that to happen, make sure you give me a little feedback about how these are actually useful. Okay, thanks, bye.